Welcome. The topic we'll be discussing in this lecture is signed multiplication. So in the last class we have discussed about multiplication of unsigned and positive numbers. In this lecture we'll be discussing how to multiply signed numbers, especially when negative signs are included. Okay. So first we'll be discussing like manually how to multiply when the multiplicand is negative and the multiplier is positive. And then we'll be discussing how to multiply two numbers when the multiplicand is negative and the multiplier is also negative. Then we'll be discussing a special algorithm for called Booth's algorithm for multiplication, which follows the same logic to multiply both positive and negative numbers. This Booth's algorithm uses the same rule to multiply positive numbers and also to multiply the negative numbers. Right? That is there can be any combination of multiplicand and multiplier, like one negative, one positive, or both positive or both negative, but it follows the same rule, right? And the prime advantage of Booth's algorithm is the number of additions that will be done will be less. Number of additions means what? Multiplication is nothing but repeated additions. Okay. So the number of repeated additions that will be done in a normal multiplicand that will be done in a normal multiplication will be more when compared with the Booth's algorithm. In a typical Booth's algorithm, the number of multiplications that will be carried out will be minimized. So that is how the Booth's algorithm was designed. Okay. So if you so why should we minimize? You may ask, why should we minimize the number of additions? So if you minimize the number of additions, what happens in the sense you are not applying the load on the processor. So the processor load is reduced. Okay. So this operation can be done at a faster rate, right? So this will actually help in increasing the speed of the processor. Okay. Say for example, when you perform multiplication in a normal way, the number of times the multiplicand should be added, the repeated addition, say if it is 50 times, okay, in the normal multiplication, when you follow, if it is 50 times the multiplicand should be added to get the result. But if you follow Booth's algorithm, if it is reduced to 10 times, then there is a drastic improvement, right? Okay. So drastic improvement. So in the sense that uh, we are unnecessarily not loading the processor. So the instruction can be executed in a faster rate. Okay. So we may not be able to sense this speed with one instruction, but if you take a typical computer, it may perform millions of operations per second. It may perform multiple operations per second. So when there are many multiplications are being carried out simultaneously, or with a very little gap between one operation and another operation, this will have a heavy impact on the speed of the processor. Okay. So that is the advantage, right? And is there any limitation with respect to Booth's algorithm in the sense? Actually, Booth's algorithm will give better performance if there are consecutive ones in the multiplier. So better performance means what? Better performance means the number of additions will be reduced. The number of additions will be reduced when there are consecutive ones in the multiplier. Okay, if there is no consecutive ones in the multiplier, then the number of additions may increase. Okay, right? So first let us try to understand the signed multiplication. Let us take these two numbers minus 13 and plus 11, how it is getting multiplied. So whenever you want to represent a negative number, it should be represented in 2's complement form. So this is actually the 2's complement representation of 13. Okay. How will you represent binary 13? Binary 13 is represented as 1101. This is the 8421 code for binary 13. Okay. But what is before this? Because we need these bits. So before this, actually we have infinite number of zeros. 0 0 like that. Full zeros are there. Okay. Now what is how will we represent this 13? So this is 13. How do you represent this in as a negative number? In the sense you have to take the 2's complement of that. So what is 2's complement? 2's complement is nothing but adding 1 with 1's complement. So first take 1's complement for this. So what is meant by ones complement? Ones complement means convert all ones to zeros and all zeros to 1. So this 1 will become 0. Okay, this 0 will become 1. Right? This 1 will become 0. This 1 will become 0. Okay, and before this we have infinite zeros in a positive 13. Okay, but when you want to convert to negative by 2's complement form, so when you take 1's complement, all these infinite zeros will be now converted to infinite ones. Okay, fine. Now to this add 1. To this add 1. So when you add 1, what you get is called as the 2's complement representation of that particular number in negative form. Okay, 0 plus 1 is 1. This is just 1. This is 0. This is 0. Okay, followed by that we have infinite ones, right? But all these infinite ones, it represent only one thing. It represents the sign of the number. So we call this as sign extension. All this infinite one is just called as what? Sign extension of this particular number. What is this number? This is the 2's complement representation of number 13. And what is its sign? That can be understood by this. All this infinite one just represents the sign of that number, and this infinite one is called a sign extension of this number. Okay, so it just says that it is a negative number, that's all. Okay, and the number is 13, so it means that it is minus 13. Okay, so we don't need all these infinite ones, we will take only the one, the first one alone we will take. Okay, so this number can be represented with 5 digits. Okay, 10011. So that is what we have represented here. So this is nothing but the 2's complement of minus 13, right? Fine. Okay, now this is the multiplicand. Now the multiplier is what? Multiplier is 11. 11, we will not take any 2's complement, we will just represent 11 in binary. So if you represent 11 in binary, this is what you get. Okay, uh, this is the equivalent 8421 code. That is, it's a 4-digit number only. We are representing using 4 bits. Okay, that last bit is, as it is a 2's complement, it represents the sign of the number. Okay, so when you represent, so 11 in binary, you will get 1011. Okay, so as the previous number has 5 bits, we added this 0 here. Now perform multiplication. So if you perform multiplication, what you will get? Multiply this 1 with this, so you get same thing, 10011. Okay, 10011. Okay, again multiply 1, so again 100. It's normal multiplication, right? Nothing. Okay, again multiply with 0, so you get zeros. 0 0 0 0 0, 5 zeros. Again multiply with 1, so you get 10011. 10011. Okay, again multiply with zeros, you will get 5 zeros. 1 2 3 4 5. Okay, now perform the addition. Okay, but before performing the addition, we have to be careful. We should extend the sign of the number. So if you extend the sign bit of this number, this sign is 1, so you will get a 1 here, you will get a 1 here, you will get a 1 here, and you will get a 1 here. Again, if you extend the sign of this number, you will get 1 here, you will get 1 here, you will get a 1 here. Okay, if you extend the sign of this number, this is 0, so for 0 there is no sign. Okay, so 0 0. If you extend the sign of this number, you will get 1 here, right? Fine. So now what we can do in the sense, now we can perform the addition. Okay, now you just add. So this is 1. Okay, this is 1. This is 1 plus 1 is 0. Carry 1. Again 1 plus 1 is 0. Carry 1. Again 1 plus 1 is 0. carry 1. Again 1 plus 1 is, yeah, 1 plus 1 is 1 0. Actually 1 plus 1 is 1 0, so we are writing 0 and carry 1. So 1 plus 1 is 1 0, plus 1 is 1 1. Okay, so 1 carry 1. Okay, 1 plus 1, 1 0, plus 1 is double 1, so 1 carry 1. Again 1 plus 1 is 1 0, plus 1, that is a double 1, that is 1 carry 1. Okay, so again what, 1 plus 1 is 1 0, plus 1 is double 1, double 1 plus 1 is what, double 1 plus 1 is 1 plus 1, 1 0, carry 1. Again 1 plus 1 is 1 0, right? So it is 1 double 0. Okay, 1 plus 1 is 1 0, 1 0 plus 1 is double 1, double 1 plus 1 is 1 double 0. So 0 and carry 1 0, 0 and carry 1 0. So 1 0 plus 1 is double 1, double 1 plus 1 is 1 double 0. Okay, 1 double 0 plus 1 is 1 0 1, 0 1. Okay, that you get 1 0 1, right? Discard that remaining thing, right? So this is the thing you are supposed to get. Okay, right? So yeah, okay, so yes, right? So we can extend this to one more level, right? We can extend this to one more level, because finally we need 10 digits. Here if you see 1 2 3 4 5 6 7, 1 2 3 4 5 6 7 8 9, only 9 digits are there. Okay, but we need 10 digits, because 10 bits we need, because input contains 5 bits, both multiplicand has 5 bits and multiplier has 5 bits, so we need one more bit. So we'll continue this for one more time, this addition. So extend the sign bit. So here this will be 1, this will be 1, this will be 0. Okay, this will be 1, this will be 0, right? So at last what you get, 1 0 1. So 1 and carry 1 0. Okay, 1 0 plus 1 is double 1, double 1 plus 1 is 1 double 0. Again 1 double 0, again 1 double 0 plus 1 is 1 0 1. So 1 and discard the remaining thing. Okay, so what you get is double 1 0 triple 1 triple 0 1. Okay, fine, let me clear the thing. So this is the final output you got, double 1 0 triple 1 triple 0 1. Okay, right? Now actually this final result is also in 2's complement notation. This final result is also in 2's complement notation. Okay, uh, and we know that it is a negative number. To actually interpret it, you have to again convert it to a regular number. So take the 1's complement of this first. So that is, convert all 1's to zeros and all zeros to 1's. So this is 0 0 1 triple 0 triple 0 1 1 1 0. Okay, right? Now add 1 to this. Now add 1 to this to get the 2's complement. Okay, so 1 1 1 1, right? Again this is 0 0 0 1. That's it. Before things are 0, right? Whatever it may be 0. Okay, so now you convert this to decimal. Okay, but we know that it's a negative number, it's not a positive number, so convert this to decimal. So this is 2 to the power 0, 2 to the power 1, 2, 3, 4, 5, 6, 7. This is 2 to the power 7. This 2 to the power 7 is what? This digit is 2 to the power 7, which is 128. 2 to the power 7 is 128. Okay, right? So this last 4 digits are 1. Last 4 bits are 1, which is nothing but 15. Okay, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Okay, so that is 2 to the power 0 is what? 1, 2, 4 and 8. Okay, right? 1, this is 1. Okay, this is 4, this is 8, this is yeah, 1, 2, 4 and 8, which is nothing but 15. So basically this 4 1 is nothing but 15. Okay, So this is 15. So this is 2 to the power 0, that is 1. Okay, this is 2 to the power 1, that is 2. This is 2 to the power 2, that is 4. Okay, this is 2 to the power 3, that is 8. Okay, 8 plus 4, 12. 12 plus 2, 14. 14 plus 1, 15. So 128 plus 15 is 138 plus 5 is 143. Okay, but 143, this is a negative number because it's a 2's complement representation. Okay, so this is how we multiply when the multiplicand is negative and the multiplier is positive. Next we shall see how we will perform the multiplication when the multiplicand is when both the multiplicand and multiplier are negative numbers. So let us take the same number. Say the multiplicand is minus 13 and multiplier is minus 11. Okay. Now 13 in binary is this 0 1 1 0 1. Okay. Now minus 13 means you have to represent in 2's complement. So take 2's complement of 13 like how we did already. First take 1's complement, that is convert all 1's to 0's and all 0's to 1. So if you take 1's complement for this is what you will get. This 0 will become 1, this 1 will become 0, this 1 will become 0, this 0 will become 1 and this 1 will become 0. Okay. Now add 1 with that 1's complement to get the 2's complement. So this is the 1's complement part. To this you add 1. So you get 1 1 you call 1 0 0 1 1. Okay, right? So previously we added 1 0 because this is the sign extension, right? Actual binary part is what? Without 2's complement is 1 1 0 1. This 0 we added because we want to represent it as negative number. So sign extension is required. Okay. So when you convert this to 1's complement, you get this 1. This is also sign extension. Okay. So in 2's complement also this sign extension continues. Fine. Similarly, convert 11 also in 2's complement form. So first represent 11 in binary. So this is the how will you represent 11 in binary? 1 0 1 1. This is 8, this is 2, this is 1. 8421 code. Okay. We are adding this preceding 0 for sign extension. Then take 1's complement of 11, convert all 1's to 0's and all 0's to 1. Then add 1. As a result, after adding 1, what you get is 1 0 1 0 1, which is the 2's complement of 11. Okay. So now what you want to multiply is 2's complement of 13 is what? 1 0 0 1 1. Okay. Right. And 2's complement of 11 is what? 1 0 1 0 1. 1 0 1 0 1. Okay. Right. But here another important thing you have to do, you have to multiply how many times means twice the number of bits of the multiplicand and the multiplier. Okay, the multiplicand contains how many bits? 5 bits. Okay, so you have to, if the multiplicand and multiplier contains whichever the maximum bits it contains, that into 2 times you have to perform the operation. Okay. So here the multiplicand contains 5 bits and multiplier also contains 5 bits. So you have to multiply for 10 times. So we are extending this sign extension for another 5 times. Right? All these are filled with ones. Similarly here also the signed multipliers, I mean the signed extension is extended for another 5 times. Okay. Now you perform the multiplication. When you add one, when you multiply 1 with this, you will get the same thing, right? Whatever the multiplicand you will get. Again when you multiply with 0, you will get the same thing but shifted to the left. Again when you multiply with 1, you will get the multiplicand shifted to the left. Again when you multiply with 0, you will get 0. Okay, all zeros shifted to the left. Again when you multiply with 1, you will get the multiplicand shifted to the left. So there are how many ones? 1, 2, 3, 4, 5, 6. So 6 times you are multiplying and it is shifted to the left. Okay. Finally, add all these things. But how many times you should add? This is keep on going. There is no end. Here also you can extend the sign bit. Okay. So you may ask how long we should do. So how long in the sense you need, if you see actual input contains how many bits? 5 bits. Okay. So the multiplicand and the multiplier are 5 bits. So the output we need only 10 bits. So you can stop from 10th bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, after reaching the 10th bit, you can stop. No need to continue further, right? So add here 1, 1, all this as per the normal rule you add. Finally what you get is the result. Okay, but this result is not in 2's complement form. Okay, only negative numbers will be in 2's complement. This is a positive number, right? So this you can see, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 3, 4, 5, 6, 7. So 2 to the power 7 is 128 plus this is 15. So this is nothing but this is equal to actually 143. This will give the direct result, right? Positive numbers will be represented directly. Okay. So this is how we multiply two negative numbers manually. Two negative numbers. So this is the core understanding of sign multiplication. Okay. With this understanding, let us move on to Booth's algorithm. So whatever I have explained here, I have explained in the notepad. That's what being told here. So in the Booth's algorithm, so as I told already, the primary advantage of Booth's algorithm is the number of times the multiplicand will be added will be reduced when compared with the standard procedure. Okay, so so in a Booth's algorithm, how many times the shifted version of the multiplicand are added when compared to the standard procedure. When you compare that with Booth algorithm, the Booth algorithm will reduce the number of repeated additions. Okay, and especially it will reduce the number of repeated addition to a larger extent if the multiplier contains consecutive ones. This is one typical example of a multiplier. Here you can see the multiplier contains consecutive ones. Okay, right? So mainly if the multiplier contains consecutive ones, then the number of shifted additions that is performed on the multiplicand will be reduced. Okay, fine. So this is just a normal multiplication. Okay, so this is one particular number. Okay, this is multiplied with another number, and this is the result you are getting. Fine. So what is this number? If you want to know, uh, actually we can identify what is that. Let me open the calculator. You can also calculate manually, but it will let me anyway. Calculator is required. Let me open that. So this is the programmer calculator I have opened. Okay. So the number is what? Multiplicand is 101101. Okay. So let me choose binary 101101. Okay. So it is decimal 45. In decimal that number is 45. Okay. And the multiplier is what? 4 1 followed by a 0. Okay. 4 1 followed by a 0. Trailing zeros, I mean the preceding zeros you can ignore. Okay, you cannot also type here 0 0, it won't come. Okay, so what should you? 4 ones, 4 ones followed by 0. Okay, so that is nothing but decimal 30. Okay, so it is the multiplication of decimal 45 with decimal 30, right? And this is the result you are getting. This is a positive multiplication, so it's a direct result, right? So the result is what? This is 10101 triple zero double 1 0. Okay, which is nothing but decimal 1350. Okay, 1350. That is when you multiply what? When you multiply when you multiply 45 with 30. Okay, right. Let me multiply 45 in decimal. 45 into 30. Okay, right. So 1350. That is what we got, right? So this is nothing but 1350. Am I correct or not? Previously, yes. What this result is what? 1 1 0 1 0 1 triple zero double 1 0. This is nothing but 1350. Okay. So this multiplication you can do. This already we have discussed. So you can check. This is the normal multiplication. Okay. But from this, what Booth has inferred from this? What is the intuition? Okay. That is what we are going to learn in this particular lecture mainly. Okay. So what Booth is here? Okay. Here if you see how many additions are going on. Here if you see how many additions are going on. This wherever there is zeros you can ignore because there is no addition there. Are you getting? Because it won't change the result. Whatever the previous partial product, that will be carried on. So whenever there is a zero, we are not going to add. If you recollect the sequential circuit also, in sequential circuit also how multiplication happened, if you recollect that, whenever the least significant bit is a zero, we won't add, okay, we won't add, we just shift. So so, so that is also because you need not add, because whatever the previous partial product, that same thing has to be carried on. Okay. So here also if you see, the point I'm trying to make is, only if there is zeros there is no addition. So here there is zero, no addition. Here there is a complete zeros, there is no addition. Here there is complete zero, so there is no addition. So totally how many times the multiplicand is added, in the sense 1, 2, 3, 4 times the multiplicand is added. Okay, 4 times the multiplicand is added, right? So is there any way to reduce this? That is the intuition behind Booth's algorithm. Okay. So if you reduce this, what will happen? Processor's efficiency will be increased and the speed at which it is executing will be increased. Okay. So to reduce that, what Booth has observed, in the sense, how why it is 4, why it is not 3 or 2 or 1, it is actually equal to number of ones in the multiplier, number of number of ones in the multiplier. This is a binary number, so it will be either 0 or 1. So you can see here how many consecutive ones are here. 4 consecutive ones. Okay. So it's not only consecutive ones, it actually number of ones, that many times we will add. Okay. But if it is a consecutive in nature, then Booth's algorithm will perform better. Okay. Now we have not gone into Booth's algorithm. Now we are just analyzing the existing multiplication. Okay. So here you can see there are 4 ones. Okay. So as there are 4 ones here, 4 times addition is going on. 1, 2, 3, 4. No more than 4 times addition is going on. Okay, remaining bits are 0. So they are not included in the addition part. Right? I think it's clear. Okay. Now is there a way to reduce this? Can we, I mean, we are adding only 4 times. The multiplicand is added first, then second, then third and fourth. Is there any way to reduce this uh, number of addition? Is there any way to reduce this number of addition? That is what Booth's algorithm concentrates. Okay. So what Booth's algorithm says, in the sense, this number is what? 30. 30. Okay. So Booth's algorithm says that instead of seeing this as 30, you see this as 32 minus 2. Instead of seeing this as 30, Booth's algorithm say that you see this as 32 minus 2. Because 32 minus 2 is also equal to what? 30. Okay. But how do we represent this in 32 minus 2, in the sense? So Booth has introduced a different notation. Booth has introduced a different notation which is something quite different. Okay. So I can write this number something like this: 0, 1 followed by 3 zeros, 1, 2, 3. Okay. And then minus 1. Normally we don't use minus 1, but this is for allowed for Booth representation. Minus 1 and 0. Okay. Now you see this is 2 power 0. Okay. This is 2 power 1. This is 2 power 2. This is 2 power 3. This is 2 power 4. This is 2 power 5. Okay. What is 2 to the power 5? What is 2 to the power 5? What is 2 to the power 5? Yes. So 2 to the power 5, I think it should be 35, 32, right? 2 to the power 5 is 32. Okay. So so this, so 2 to the power 5 is what? 32. Okay. So this digit, this one represents to 32. This is what? 2 to the power 1. 2 to the power 1 is what? 2. 2 to the power 1 is 2. But there is a minus sign here. So it is minus 2. It is minus 2. Okay. So this is what? So this is equivalent to 30. This is equivalent to 30. You getting? So Booth says that instead of seeing this as 32, instead of seeing this as 32, you see as 32. Sorry, instead of seeing this as 30, instead of representing 30 directly in binary, instead you represent as 32 minus 2. So how to represent means Booth says that you represent like this. You getting? Okay, if you represent like this, what will happen? What will happen in the sense number of ones is reducing. Now in this representation, how many ones we have? Only two ones. 1, 2, only just two ones. Whereas in the previous representation, how many ones were there? 4 ones were there. So if there is only two ones, then the number of addition will be reduced. So only 2 times you have to add. Okay, right? So this is the core logic behind Booth's algorithm. Let us see how it fully works, right? So so basically what Booth says in the sense, in our case, this is the multiplier which is equal to 30, but Booth says that instead of seeing this as 30, you consider it as 32 minus 2. Okay, so when you see it as 32 minus 2, it can be represented like this. When you see it as 32 minus 2, it can be represented like this. Okay, 1 0 0 minus 1 0, right? 1 0 0 minus 1 0. Okay, so this 1 is nothing but 2 to the power 5. 0 1 2 3 4 5. So this 1 is 2 to the power 5. And what is this one? This is 2 to the power 2 to the power 1, and there is a negative sign is there. So this is 2 to the power 5 is nothing but 30. So it is 30 minus 2, which is nothing but, sorry, 32 minus 2. 2 to the power 5 is 32. 32 minus 2, which is nothing but 30. Okay, right. Now there is a negative number, negative minus 1 is included. So how we will perform multiplication, that we will see. Okay. So first bit is 0. So when you multiply with this, you will get 0. So all these are zeros. Fine. Okay. Second is minus 1. When you multiply this entire thing with minus 1, what you will get? You will get minus of this particular number. Okay. When you multiply x with minus 1, you will get what? Minus x. So this entire thing, if you treat as x and if you multiply with minus 1, still it is binary, but you will get minus of this. Okay. And how negative numbers are represented in uh, binary? It is represented in 2's complement. So just take 2's complement of this. Okay, or you can include this previous 0 also. Take 2's complement of this. So for taking the 2's complement only, this previous 0 we added. Okay, so this is the multiplicand, 0 1 0 or double 1 0 1. So 2's complement means convert all ones to, first take 1's complement by converting all ones to zeros and zeros to 1. So 1 0 1 double 0 1 0. Okay, 1 0 1 double 0 1 0, right? Then add 1. Then add 1 to this. 0 plus 1 1 1 0 0 1 0 1. Okay, 1 1 0 0 1 0 1, right? So what you get is 1 0 1 double 0 1 1. Okay, so you can see that is what here we have written 1010011. This is nothing but the 2's complement of this multiplicand, right? Okay, like that continue. Next is 0. So there is nothing but filled with zeros. Next is zeros, filled with zeros. Next is 0, again filled with zeros. Next is 1. So this is not a negative one, this is a positive one. So just copy the multiplicand. So which is 0 1 0 1 1 0 1. So 0 1 0 1 1 0 1. Okay. Next is 0. Again fill up with zeros, right? Now finally we need the result to have at least 10 digits. Okay. So yeah. So result should have how many? Yeah, this has 1 2 3 4 5 6 7. So result should have 14 bits. 1 2 3 4 5 6 7 bits. Okay, because multiplicand and multiplier each having 7 bits, so result should have 14 bits. Okay, so that many times you have to extend the what you call sign bit. Okay, here if you see 7 1 2 3 4 5 6 7, so another 7 zeros we are adding 1 0 1 2 3 4 5 6 7. Okay, for 0 there is no sign, so it is extended with 0. For all, if the number is not zeros, then extend the sign bit, that is 1. 1 is extended here. All these are zeros, so extend these zeros. Okay, right? Okay, here if you see, this is a positive number, this is a positive, this is not a, this is a negative one. Okay, this is the negative one, so here alone we are extending 1. Okay, here alone we are extending 1, whereas this is a positive number, this is positive 1 is multiplied with this, so here we are not extending the uh, extending 1 here. Okay, here sign is 0 only, right? Okay, then you add, right? Okay, so after performing addition, whatever the result you get, okay, whatever the result you get, that is the yeah, that result, uh, so this is the result you are getting. Okay, so this is actually again the 2's complement of the actual result. Okay, so what is the result, what should be the result by multiplying these two? So if you see, it is what which are the numbers we are multiplying is actually, this is the multiplier, multiplicand 1011. I'll take the programmer's binary, 101101. Okay, the decimal equivalent is 45. Okay, so same number, it is 45 into 30. Okay, so 45 into 30 is, what is the result previously we got? 45 into 30, 1350. It should be 1350. Okay, so the result is, yeah, yeah, this is the result. The result is not in 2's complement, this is normal result. Okay, you need not take, the result is not in 2's complement, so previously I said it is in 2's complement. Actually Booth's algorithm does not give the result in 2's complement form, it gives the exact result. Okay, this result is equal to what? The result, actual result, you need not change anything. This is equal to 1350, right? So this is how the Booth's algorithm works, right? So now here in this, if you see how many additions are being done, means only 2 additions. This is one addition, this is one, and this is the second time. There are only 2 additions carried on. Okay, so it has reduced the number of additions when compared with the normal approach. Okay, but Booth's algorithm can reduce the number of additions only if there are consecutive ones in the multiplier. Okay, fine. Okay. So here we have seen both positive numbers, right? These both two are positive numbers, right? But if there is a negative number, then how it will be done? That also we will see. Okay. So see this case here, one number is actually negative number, right? One number is actually a negative number. So you want to multiply 13 with minus 6. You want to multiply 13 with minus 6. Okay. So, so how do we go about that? Okay. So first you have to 13 should be multiplied with minus 6. Okay. So how can you represent minus 6? So here if you see how it is represented, first we are taking 2's complement of 6. First you should take the 2's complement of 6. Okay. What is the 2's complement of 6? What is the 2's complement of this is what we want to perform, right? Okay, so this here it is represented in the 2's complement, right? So 6 is 6 in the sense it is uh, 0 double 1 0. Okay, 0 double 1 0. If you take 1's complement, it is 1 double 0 1. Okay, 1 double 0 1, right? Then add 1 to this. So 1 plus 1 is 0. I mean 1 0 0 and carry 1. So 1 0 1. Okay, so 1 0 1 0. So before this there is zeros are there, so that will be converted to 1. Okay, so that 1 will come here. This is sign extension, so there are infinite ones. So as a result you got this 1 1 0 1 0. So this is the what you call 2's complement representation of minus 16. Okay, but how Booth will see this? So Booth algorithm, what it will do, so here again if you see there is a minus 1 here, there is a plus 1 here, there is a minus 1 here. Okay, so this is what 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3. Okay, so so let me erase this. 2 to the power 1 is what? 2 to the power 1 is 2. 2 to the power 1 is 2, but this is what? Minus 2. This is minus 2. Okay, 2 to the power 2 is 4, but this is plus 4. This is plus 4. 2 to the power 3 is 8. Again, this is minus 8. Okay, so minus 8, minus 8 minus 2 is minus 10. Minus 10 plus 4 is minus 6. You get it? Okay. Actually, it is nothing to do with this 2's complement. Even you need not see this. This is just minus 6. It is represented here as 2's complement, but this part is not required for us. Don't confuse this. This is no way connected with Booth's algorithm. This 13 you just represent in binary as it is 1101. Okay, this 6, how in Booth's algorithm it can be represented. There are various ways. So how this coding is done, that we'll be discussing later. Okay, but one of the ways what you can call it as minus 8 plus 4 and minus 2. Okay, if it is minus 8 plus 4 and minus 2, then this is the logic. Okay, so this part corresponds to minus 8, this corresponds to plus 4, and this is minus 2. So which is nothing but, it is nothing but minus 6. Okay, so we got this minus 6, right? Now perform multiplication, right? So this is 0, so fill up here with zeros. This is minus 1. So whenever there is minus 1, what you have to do? Take, this should be multiplied with x. Okay, so there is minus x, so this should be represented in 2's complement. Okay, so what is the 2's complement of this 0 1 1 0 1? Its 2's complement is, first take 1's complement 1 0 0 1 0 and add 1 to this. So 0 plus 1 is 1, again 1 0 0 1. So it is 1 double 0 double 1. Okay, so that is what copied here, 1 double 0 1 1 with one shift. Okay, again there is a positive 1, so you will get just same thing, 0 double 1 0 1. Okay, so 0 double 1 0 1. Okay, again there is a negative 1, so when you multiply you will get this 1 double 0 1 1. So 1 double 0 1 1. Again there is 0, so when you multiply this to this you will get zeros. Okay, so this input contains how many bits? 5 bits. 1 2 1 2 3 4 5. Both multiplication and multiplier contains 5 bits. So the final output we need 5 bits. So here there are 5 bits, 1 2 3 4 5, but we are extending another 5 bits, 1 2 3 4 5. Okay, wherever there is a negative number, this 1 should be extended there. So this is a negative part. Okay, so here 1 is extended. This second one is a positive part, so here 0 is extended. The third one is again negative part, so again here 1 is extended, right? And finally add everything. Finally add everything, right? So when you add, you got this. Okay. Finally, when you add, what you get? This is 0. Oh, this is 1. Okay. This is 1 plus 1 is 1 plus 1 is 1 0. So 0 and carry 1. 1 plus 1 is 1 0. So 0 carry 1. 1 plus 1 is 1 0 plus 1 is 1 1. So 1 and carry 1. 1 plus 1 is 1 0 plus 1, that is 1 1. So 1 and carry 1. 1 plus 1 is 1 0, so 0 and carry 1. 1 plus 1 is 1 0 plus 1 is double 1, so 1 and carry 1. 1 plus 1 is 1 0 plus 1, so double 1, so 1 and carry 1. 1 plus 1 is 1 0 plus 1, so 1 remaining you can ignore. Okay, so you know that this result will be a negative result. So see, the thumb rule is if the result is negative, it will be in 2's complement form. Okay. If it is a positive result, it will be a direct number. Okay. In the previous case, if you see, it is a positive result, right? We are multiplying 30 with 45. We are multiplying 45 with 30. So the result is also positive number, so it is appearing directly positive. Okay, but here the result is a negative number. So actually it is in 2's complement form. So to interpret this, you have to convert to 1's complement. Okay. You have to again convert to 2's complement. So first convert to 1's complement. So all zero, all convert all ones to zeros and zeros to 1. So triple zero, 1, double zero, double 1, 0, 1. Okay. Okay. Again add 1 to this. So if you add 1 to this, 1 plus 1, 1 0. So 0 carry 1. So 1, 1, 1. Okay. 0, 0, 1, and the previous things are 0, right? Now let us see what is this. This is 2 to the power 1. This is 2 to the power 2. This is 2 to the power 3. 2 to the power 4, 5 and 6. Okay. 6. Okay. So previously we have seen that 2 to the power 5 is 32. Okay. So 2 to the power 6 is 64. 2 to the power 6 is nothing but 64. Okay. 2 to the power 3 is 8. 2 to the power 3 is 8. Okay. 2 to the power 2 is 4. 2 to the power 1 is 2. So add all these things. So this is 2 to the power 1 is 2. So 8 plus 2, 10. 10 plus 4, 14. Okay. 64 plus 14 is 78. Okay. And we know that it's a negative number and it is in 2's complement, so this minus sign comes. Okay. So this is how the Booth's algorithm works for negative numbers, right? Fine. So now how this coding is done in the Booth's algorithm. We have discussed two algorithms, two problems where we have just assumed that this minus 6 is represented as minus 8 plus 4 and minus 2, all these things. And in the previous problem we assumed that 30 is represented as 30 minus 2. Okay. But actually, is there any other way to do this coding in the sense? Yeah, there is a logic. So the logic, what it says in the sense, let us assume this is the multiplier. This is the multiplier. So we are modifying the multiplier only, right? Let us assume this is the multiplier. Then what you should do in the sense, scan the multiplier from right to left. Scan the multiplier from right to left. Okay, that is from here to here. In this direction, you have to scan. Okay, fine. Before scanning, you should do one thing. Assume that there is one extra zero is here. Assume one extra zero is here. Okay, and then this is the rule. whenever you move from 0 to 1, whenever you move from 0 to 1, uh, that respective bit should be replaced with minus 1. Okay. And whenever you move from 1 to 0, that respective bit should be replaced with 1 1. Okay. In all other cases, the respective bits will be replaced with 0. Right. That is, if it is 0 0, okay, if you in the multiplier, if it is 0 0, then we will replace that with, I mean, the corresponding bit will become 0. Okay. If it is 0 1, the next bit will be, in the multiplier, it will be replaced as minus 1. Okay. If it is 1 0, it will be replaced as 1. Okay. If it is 1 1, if it is if it is 1 1, it will be replaced as 0. Okay. So that is what we are going to do. So we added one at the to the right, we added one more 0. Now compare these two. This added rightmost 0 and the rightmost bit. Okay, that is the least significant bit of the multiplier. What is this? Both are 0. Both are 0 means it will be 0. Okay, so this becomes 0. Right? Okay. Next, compare these two bits. 0 0. So again 0. Next, compare these two bits. 0 1. If it is 0 1, what should you do? It will be minus 1. It will be minus 1. So 0 1. So this becomes minus 1. Next, 1 1. If it is 1 1, it should be what? 0. So this bit becomes 0. Okay. Next, 1 0. If it is 1 0, it should be 1. Whenever it is 1 0, it is 1. Okay. So this is 1 0, so this becomes 1. This is 0 1, so this becomes minus 1. Again 1 0, so this becomes 1. Again 0 1, so this becomes minus 1. This is 1 1, so this becomes 0. Again this is 1 1, so this becomes 0. Okay. Again this is 1 0, 1 0 is 1, so this becomes 1. Again this is 0 0, so this becomes 0. Okay. This is 0 1, so 0 to 1 means it is minus 1, so this becomes minus 1. Again 1 1, so 1 1 means 0, so this is 0. Again 1 0, it is plus 1. Okay. 0 1, this is, so this is replaced with minus 1. Again 1 0, this is replaced with plus 1. Again 0 0, it is replaced with 0. Okay. So this is how we do this coding, right? So this is how we do this coding. Okay. So now you can take our previous example. You take this 0 0 4 1 0. Okay. 0 0 4 1 1 2 3 4 4 ones and 0. Okay. So to the right side, you should add one more 0 as per the algorithm. To identify the correct code, to the right side you should add 1 0. Okay. So what is the logic? 0 0 means that bit position will become 0. Okay. 0 1 means it will become minus 1. So here we will get minus 1. Okay. 1 0 means 0. Right. 1, yeah, 1 1 means 0. Again 1 1 means 0. Again 1 1 means 0. Again 1 0 means whenever you move from 1 to 0, it becomes 1. It becomes 1. Okay. 0 0 is 0. Okay. Now you check our code. How we got this code? 0 plus 1 triple 0 minus 1 0. This is that code. Okay. So if sign is not mentioned, it is plus. Right. Okay. So like that you can check for the other number also. To take this uh, this particular number. Okay. So this is, yeah, this is the number, right? So this is the 2's complement representation of 6. This is the 2's complement representation of 6. 1 1 0 1 0. Okay. So how we got this particular thing in the sense, again to the right you add a 0. Again to the right of this you add a 0. Okay. Now what is this? 0 0 means 0. When you go from 0 to 1, minus 1. Okay. When you go from 1 to 0, plus 1. Okay. When you go from 0 to 1, minus 1. Okay. When you go from 1 to 1, 0. Okay. So you can compare 0 minus 1 plus 1 minus 1 0. So this is how we got. Okay. So this is how Booth coding is done, right? So that is what being explained here, right? And this particular table actually shows how Booth coding is done. Already I have explained you. If bit I is 0 and I minus 1 is 0, then it will be 0. Okay. If bit I is 0 and bit I minus 1 is 1, that is when you are moving from right to left. Okay. So this is ith bit. Okay, this is I minus 1th bit, like that. This is numbered. Okay. So rightmost is first, then second, then third. Oh, sorry. Or bits are normally numbered from where to where. Bits are normally numbered from yeah. So here it is numbered. Actually, this ith bit is the highest bit. Okay. Okay. So it is basically you have to move from right to left. Okay. If this is what you call, if this is then 8th bit, if the I mean the rightmost bit is 8, then next will be 7, then 6. With this understanding, this I and I minus 1 you have to take. Okay. So if it is 0 0, it will be replaced with 0 into multiplicand. If it is 0 1, plus 1 into multiplicand. If it is 1 0, minus 1 into multiplicand. If it is 1 1, 0 into multiplicand. Right? So that's it about Booth's algorithm. So when Booth's algorithm will perform better and when it will perform worse, in the sense, Booth's algorithm will perform worse if the input contains a combination of zeros and ones or alternating zeros and ones. Booth's algorithm will perform worse if the input contains alternating zeros and ones. Okay, and it will perform in a better way, in a best way, if the input contains continuous ones. Okay, continuous ones. Say this is an example where there is alternative 0 and 1s. 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1. Okay. Now what will be the how the multiplier will be modified, in the sense we will assume 1 0 here. So this is 0 to 1, this becomes minus 1. Okay. 1 to 0, this becomes plus 1. 0 to 1 minus 1. 1 to 0 plus 1. 0 to 1 minus 1. So alternatively you are getting minus 1 plus 1 minus 1 plus 1. So this means what? You have to do this many addition. This many addition. Are you getting? Even in the normal number, that many addition is not happening. Even if you don't use Booth's algorithm, in this case the number of addition will be less. Okay, this contains how many bits? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. 15 bits. In normal time also it will have only, in normal multiplication also it will have only 1 2 3 4 5 6 7. Only 7 addition will be there. But if you do here, if you apply Booth's algorithm, it will perform 15 additions. Okay. So actually in this scenario, Booth's algorithm performs worse than the normal multiplication. Repeating. Okay. And this is an ordinary case where there are not consecutive ones, some random positions there are ones. Okay. So again the logic is same. Add one rightmost 0, 0 0 it is 0, 0 0 it is 0, 0 1 minus 1, 1 1 0, 1 1 0, 1 1 0, 1 0 plus 1, like that. Okay, right? Here if you see how many additions in the normal case and in the Booth's algorithm case. In the normal case it is 1 2 3 4 5 6 7 8, 9. 9 additions will be carried out. With Booth's algorithm, 1, 2, 3, 4, 5, 6, 7. 7 additions are carried out. Okay, that is the number of additions were decreased by 2. Okay, a reasonable improvement. This is a reasonable improvement with Booth's algorithm. Okay, but if you say this case, here you can see there are consecutive ones. There are consecutive 5 ones. Again, there is consecutive 3 ones. Okay. Again, if you assume 0 here to the rightmost, so 0, 1 becomes minus 1, 1, 1, 0, 1, 1, 0, 1, 0 is plus 1, 0, 0 is 0, 0, 0 is 0, 0, 0 is 0, 0, 1 is minus 1, 1, 1 is 0, 1, 1 is 0, 1, 1 is 0, 1, 1 is 0, 1, 0 is plus 1, 0, 0 is 0, 0, 0 is 0, 0, 0 is 0. Okay. Here if you compare the number of additions that is done in normal multiplication will be 1, 2, 3, 4, 5, 6, 7, 8 multiplication, 8 additions. Number in the normal multiplication there are multiplicand will be added 8 times. Okay. Whereas with Booth's algorithm the number of additions will be reduced to 1, 2, 3 and 4, 4 just 4 times. Okay. So this is just an analysis of Booth's algorithm. That is, Booth's algorithm performs better when there are consecutive ones, and when there is alternating zeros and ones, Booth's algorithm performs in a worst way. Okay, right? So that's it about Booth's algorithm. Right? Let us stop here. Thank you.